All right, Chemistry 1411. This is practice exam 3. Question number 1, which of the following does not fit the definition of a Bronsted base? Well, we know that a Bronsted base is a proton acceptor. So we're looking for proton acceptors. And if we look at the carbonate ion, it can accept a proton, right? It can accept a proton to form the bicarbonate ion. Ammonia can accept a proton to become an ammonium ion. Water can accept a proton to become hydronium. And the bicarbonate ion can accept another proton to become carbonic acid. But ammonium cannot accept a proton. And so ammonium, the ammonium ion, is not a Bronsted base. In fact, it is a Bronsted acid. It is a proton donor. Question number 2, in this reaction, the conjugate acid-base pairs are, well, if we look at what's happening from the point of view of the reactants, you see that this molecule is behaving as an acid. This is acetic acid, a weak acid. Why is that an acid? Because if we look over here, you see that it's lost a proton. Therefore, it was behaving as a proton donor. Therefore, it is an acid. That means that this polyatomic ion here is a base. Now, if we look at the product side, we see that the acid lost a proton to give us this species here. So that makes this the conjugate base, which would render this the conjugate acid. If you ever get confused about conjugates, you can just think of the reaction going in the reverse direction, right? What is this molecule doing in the reverse direction? It's accepting a proton, therefore it's a base. And what is this molecule doing in the reverse direction? It's donating a proton, and therefore it must be an acid. And so the pairs are going to be acetic acid and the acetate ion, and then amide. NH2 minus is called amide, and NH3 is ammonia. So those are the conjugate pairs in this reaction. Number 3, which of the following is not a conjugate acid-base pair? Water and hydroxide. Those are a conjugate acid-base pair. If water loses one proton, it becomes hydroxide. The next one is water and a hydronium ion. Well, if water gains a proton, it becomes hydronium, so those are conjugates. If we look at C, these are not conjugates of one another, right? If hydronium, H3O+, loses a proton, it simply becomes water. It doesn't become hydroxide. And if hydroxide, OH-, gains a proton, again, it becomes water. It does not become hydronium, and so these are not conjugates. If we look at the next one, we see that if this polyatomic ion gains one proton, it becomes hydrogen peroxide, so these are conjugates. And if we look at O2 with a 2- charge, if it gains one proton, we end up with this as the conjugate acid. And so the answer is C. These are not a conjugate acid-base pair. Question number 4, what is the hydroxide ion concentration in a 5.2 times 10 to the minus 4 molar nitric acid solution? You need to know that nitric acid is a strong acid. It is on our list of strong acids, and therefore it is going to dissociate 100% to give us H+ ions and nitrate ions. So if it dissociates 100%, that means that if I'm starting out with 5.2 times 10 to the negative 4 molar nitric acid, when it dissociates completely, I'm going to have none of this left over, and I'm going to have 5.2 times 10 to the minus 4 molar for my concentration of my hydrogen ions, and I'm also going to have the same concentration for my nitrate ions. Those are not important to me, but I can use this concentration of hydrogen ions in order to determine my hydroxide ion concentration. I'm going to have to use the formula for Kw, which is Kw is equal to the concentration of hydronium ions multiplied by the concentration of hydroxide ions. And so Kw is the auto-ionization constant for water. If we rearrange that to solve for the concentration of hydroxide, we get that it's equal to Kw divided by the concentration of hydronium. So we have 1 times 10 to the negative 14 divided by the concentration of our H3O+. Remember that the proton, H+, is solvated in water. So H+ is the same thing as our hydronium ion. Okay? And so we just plug that in, 5.2 times 10 to the negative 4. And when we do that, we end up with a concentration for our hydroxide ions that is 1.9 times 10 to the negative 11 molar. and that is A. Question number 5, which of the following solutions are basic? Well, if we look at the autoionization of water, Kw, which is equal to 1.0 times 10 to the negative 14, which is equal to the concentration of hydronium times the concentration of hydroxide. Well, when these two concentrations are equal, we have water that is neutral. It's going to have a pH of 7. And so the concentrations of the hydronium would be 1.0 times 10 to the negative 7. And the concentration of the hydroxide would be 1.0 times 10 to the negative 7. And of course, both of those are in moles per liter. And so if we have a basic solution, we're going to have one where the concentration of hydroxide is greater than 1.0 times 10 to the negative 7. So the concentration of the hydroxide is going to have to be greater than 1.0 times 10 to the negative 7. Or put another way, the concentration of the hydronium is going to have to be less than 1.0 times 10 to the negative 7. And either of those scenarios will produce a basic solution. So we see that in A, we have the concentration of the hydroxide being much lower than 1 times 10 to the negative 7. And so that is not a basic solution. We see the next one would be neutral because the concentration of our hydroxide is exactly 1.0 times 10 to the negative 7. We see that in C, the concentration of the hydronium is less than 1.0 times 10 to the negative 7. And so that is going to be a basic solution. If we look at D, the concentration of the hydronium is greater than 1 times 10 to the negative 7. And so that is not a basic solution. In the last one, we see that the concentration of the hydroxide is less than 1 times 10 to the negative 7. So that is also not basic. You can even check this question just by evaluating the pH of the solution. pH is equal to the negative log of the concentration of the hydronium. And so the pH is going to be equal to the negative log of 1.0 times 10 to the negative 14, like that. And so when we punch that in our calculator, we get that our pH is 14. And so we have a solution that is strongly basic. Question number 6, calculate the pH of a 0.14 molar nitrous acid solution that is 5.7% ionized. Right? Nitrous acid, HNO2, is not going to ionize completely because it is not a strong acid, it is a weak acid. So if we write out our equilibrium for our nitrous acid, we have our nitrous acid, which we're going to put in water, and it's going to partially dissociate to give us hydronium ions plus nitrite ions, like that. Now if we're starting out initially with a 0.14 molar solution, the question is telling us that only 5.7% of it is ionizing. That means that only 5.7% of it is being converted to hydronium and nitrite ions. And I'm looking for the concentration of hydronium ions so that I can determine the pH. And so to evaluate what the concentration of my hydronium ion is going to be, I'm going to take my 0.14 molar and I'm going to multiply it by 5.7 divided by 100%, like that. And I end up with the amount of my nitrous acid that has been dissociated. And I end up with 0.00798 molar for the concentration of my hydronium ions. Now again, I get the same concentration for my nitrite, but I don't need the concentration of nitrite to evaluate my pH, because pH is equal to the negative log of the concentration of hydronium ions. Now I know that here I have an extra sig fig, but I'm going to round that off at the end. So I have the pH is equal to negative log of 0.00798. And when I put that in my calculator, I end up with 2.10. Right? Remember, I report the pH to 2 decimal places because they gave me a concentration with 2 significant figures. And so the pH of this nitrous acid that is 5.7% ionized is going to be 2.10. All right, question number 7. What is the pH of a 0.001 molar calcium hydroxide solution? Well, I know that calcium hydroxide is a strong base, and so it's going to dissociate completely. If I start out with my calcium hydroxide, it's going to dissociate completely to give me calcium ions, which Calcium comes from group 2A, so it's going to have a 2 plus charge. Plus, I'm going to have 2 hydroxide ions. So I'm going to produce twice the amount of hydroxide, so 2 times OH, like this. So if I'm starting out with an initial concentration of my calcium hydroxide is 0.001 molar. I assume I don't have any of these initially. But then since I get complete dissociation, I'm going to lose all of the calcium hydroxide, and I'm going to produce calcium ions and hydroxide ions. The thing is that I'm going to produce 0.001 molar calcium ions, but I'm going to produce twice that concentration of hydroxide ions. So I have plus 0.002 in this case. So at equilibrium, I have none of the calcium hydroxide, but I have 0.001 molar calcium ions, and I have 0.002 molar for the concentration of my hydroxide ions. So if I want to evaluate the pH, first I decided to calculate the pOH using the concentration of hydroxide ions. So pOH is going to be equal to the negative log of the concentration of my hydroxide ions, which equals the negative log of 0.002. And when I punch that in my calculator, I end up with a pOH that is equal to 2.7. And so since pH is going to be equal to 14 minus the pOH, I get that it's equal to 14 minus 2.7. And when I punch that in my calculator, I get that my pH is equal to 11.3. And that is E. Question number 8, the pH of coffee is approximately 5.0. How many times greater is the hydronium concentration in coffee than tap water that has a pH of 8? Well, I know that pH is calculated as the negative log of the base 10 of the concentration of hydronium. So that means that every time the pH changes by 1, I get a factor of 10 times the change in the acidity. And so since the difference in the pHs is going to be 8.0, subtract 5.0, which gives us 3.0, that means that we take 10 to the power of 3, which equals 1,000. So that means that the concentration of the hydronium in coffee is going to be 1,000 times greater than that in tap water. Question number 9, a 5.5 liter sample of 0.25 molar nitric acid solution is mixed with a 1.2 liter of a 0.34 molar hydrochloric acid solution. And what's the pH of those two solutions after they're mixed together? Well, I know that nitric acid, HNO3, and hydrochloric acid, HCl, are both strong acids, which means they're both going to dissociate 100%. So that means that if I evaluate the number of moles of nitric acid or the number of moles of hydrochloric acid, it's going to give me the number of moles of hydronium ions. So let's figure out let's figure out the number of moles of hydronium ions from the nitric acid. So we have HNO3. We have a concentration of 0.25 moles per liter. We're going to multiply that by the volume, which is 5.5 liters. And we end up with the number of moles as being 1.375 moles. Again, I'm carrying extra sig figs, and I'll do my rounding at the end. Now that means that the number of moles of hydronium that I'm getting from my nitric acid is 1.375 moles. Again, why do I know that? Because nitric acid is a strong acid. It dissociates completely in water to give you hydronium ions and nitrate ions. So let's do the same treatment for our hydrochloric acid. So from the hydrochloric acid, we have a concentration of 0.34 moles per liter. We multiply that by the volume, 1.2 liters. And when we do that, we get 0.408 moles. Again, I'm carrying an extra sig fig here, but I'll do my rounding at the end. And that gives me the number of moles of hydronium ions from my hydrochloric acid. Why? Because I know when I take hydrochloric acid, which is a strong acid, and I put it in water, it dissociates 100% to give me hydronium ions plus chloride ions, right? So that means that we have a 1-to-1 relationship here. Now I can figure out the total number of moles of my hydronium ions. So all I'm going to do is tally these two numbers up, and I end up with 1.782 3 moles of hydronium ions. So this is equal to the number of moles of hydronium ions total. Well, in order to figure out the concentration of the hydronium ions, the total concentration, I'm going to take the total number of moles and I'm going to divide it by the total volume. So I have my total number of moles, 1.783 moles, divided by the total volume, which is 5.5 plus 1.2, which gives me 6.7 liters. And when I do that, I get that the concentration of my hydronium is 0.2661. Again, I'm carrying some extra sig figs here, and I'll round them off at the end. So when I want to calculate the pH is equal to the negative log of the concentration of the hydronium, which is equal to the negative log of the 0.2661. Again, since I only have 2 sig figs to work with from the numbers that were given to me, I'm going to report my pH to 2 decimal places, and when I work that out, I get that my pH is equal to 0.57, like that, so it is B. Question number 10. The pOH of a solution is 10.40. Calculate the hydrogen ion concentration in the solution. Well, I'm given the pOH, so what I'm going to do is calculate the pH, knowing that pOH plus pH is equal to 14. I can calculate my pH is going to be equal to 14, subtract the pOH, which is 14, subtract 10.40. That gives me a pH which is equal to 3.60. Now I need to use the formula that the concentration of hydronium is equal to 10 to the negative pH, and that should give me my answer. So I get that the concentration of hydronium ions, which is a hydrogen ion, is equal to 10 to the negative 3.60. Now notice I have 2 decimal places in my pH, and so I'll report my concentration of hydrogen ions or hydroniums to 2 decimal places, and when I put that in my calculator, I get that the concentration of hydrogen ions is equal to 2.5 times 10 to the negative 4 molar. D. Question number 11 asks, which solution will have the lowest pH? Well, we know that when we have a low pH, a pH below 7, we're going to have an acidic solution. And if I take a look at the acids here, if I look at A, I have 0.25 molar hypochlorous acid. In B, I have 0.25 molar chlorous acid. If I have 0.25 molar chloric acid in C, and then in D, I have 0.25 molar perchloric acid. Well, the thing about A, B, and C is that hypochlorous acid, chlorous acid, and chloric acid are all weak acids, and they're in the same concentration as perchloric acid, which is a strong acid. And we know that strong acids dissociate completely, whereas a weak acid is only going to dissociate partially. And so therefore, I know that D is going to have a lower pH because it's going to be more acidic than any of A, B, or C. The last one, E, is a 0.25 molar solution of sodium perchlorate. And I know that a sodium ion is not going to affect the pH. And the perchlorate ion is the conjugate base of a strong acid, and so it is also not going to affect the pH. And so the answer is the 0.25 molar solution of perchloric acid, again, which is a strong acid, is going to have the lowest pH. Question number 12 says, given the following Ka values, which anion is the strongest base? So we have some acids here. We have hydrofluoric acid. We're given the Ka of hydrofluoric acid, which is 7.1 times 10 to the negative 4. And then we're given the conjugate base of hydrofluoric acid. Next we have formic acid. We're given its Ka, and we have the formate ion here. Next we have hydrocyanic acid, and we have the cyanide anion here, which is the conjugate base of hydrocyanic acid. Next we have nitrous acid and the nitrite ion, which is the conjugate base of nitrous acid. And then lastly, we have acetic acid, and we have the acetate ion, which is the conjugate base. Well, you need to know that Kw is equal to Ka times Kb. And if we solve this for Ka, we get that Ka is equal to Kw over Kb. Now Kw is a constant at constant temperature, and so we see that Ka and Kb are inversely proportional. That means the smaller the Ka, I'm going to get a larger Kb. The smaller the Ka means the weaker the acid, and we know that the weaker the acid is, the stronger its conjugate base is going to be. Stronger conjugate base. And if we look at all of the Ka values, we see that the Ka value for hydrocyanic acid is the lowest of all these by quite a bit. And so since it is the weakest acid on the list, it is going to have the strongest conjugate base, which will be the cyanide ion. Question number 15, which of the following yields a basic solution when dissolved in water? The first one is ammonia, and we know that when we put ammonia in water, it's going to partially dissociate. Ammonia as a base, it's going to be a proton acceptor. So we're going to end up with an ammonium ion plus a hydroxide. And since hydroxide is basic, that means that ammonia is going to produce a basic solution. The next one is sodium oxide. Sodium is a metal, so this is a metal oxide. And when we put a metal oxide, like sodium oxide, in water, we end up producing sodium hydroxide, which is a base. And so that means that sodium oxide is also going to produce a basic solution when put in water. The next one is lithium hydroxide. Well, lithium hydroxide is a strong base. It dissociates completely to give us lithium ions plus hydroxide ions. And so it is basic. But the next one, tetraphosphorus decoxide, is a non-metal oxide, right? Phosphorus is a non-metal. And when we take tetraphosphorus decoxide and we put it in water, we end up producing phosphoric acid. And so it produces an acidic solution. And so the answer is 1, 2, and 3. Ammonia, the sodium oxide, and the lithium hydroxide will all produce basic solutions when dissolved in water. Number 16, which one of these salts will form a basic solution when dissolving in water? Well, we're going to have to look at the anions for each one of these compounds. So if we look at sodium chloride, the anion in A is chloride. The anion in B, potassium cyanide, is a cyanide ion. The anion in C is nitrate, the nitrate ion. The anion in D is also the nitrate ion, and the anion in E is the chloride ion. And we know that chloride and nitrate are both the conjugate bases of HCl and HNO3, both of which are strong acids. And therefore, chloride and nitrate are both going to be weak. These are going to be weak bases because, again, they're the conjugate bases of strong acids. Whereas cyanide is the conjugate base of hydrocyanic acid, which is a weak acid. And since it is a weak acid, cyanide is going to be a stronger base. And so it is going to be the strongest base of all the anions in all of these salts. And so when you put cyanide in water, it's going to act as a Bronsted base, producing hydrocyanic acid, and we're also going to produce hydroxide ions. And so that is why when we put potassium cyanide in water, we end up with a basic solution. Question 17, what is the pH of a 0.023 molar hydrocyanic acid solution? And it gives us the Ka of hydrocyanic acid, which is 4.9 times 10 to the negative 10. Well, we know that hydrocyanic acid is a weak acid, and so when we put it in water, it is only going to partially dissociate to produce hydronium ions plus cyanide ions, like that. We know that initially we have 0.023 molar of our hydrocyanic acid. We have none of the hydronium or cyanide ions. we're going to lose a certain amount of our hydrocyanic acid. We're going to produce the same amount of hydronium in cyanide ions, and at equilibrium we're going to have 0.023 here. We're going to have X here and X here. The reason I'm ignoring the minus X is because the initial concentration of my weak acid is greater than 100 times the Ka, which would be 4.9 times 10 to the negative 8. So I get that my Ka, which is equal to the concentration of hydronium times the concentration of cyanide divided by the concentration of HCN, is equal to 4.9 times 10 to the negative 10, which is equal to X squared over 0.023. I solve for my X, which is equal to the concentration of hydronium, which I'm going to need to evaluate my pH. And when I put that into my calculator, I end up with the square root of 1.127 times 10 to the negative 10. Yes, I'm carrying an extra couple of sig figs, but I'll round off at the end. I end up with 3.36 times 10 to the negative 6 molar for the concentration of my hydronium. pH is equal to the negative log of that concentration. Again, I know I'm carrying an extra sig fig, but I will round at the end, and I get that my pH, which should only have 2 decimal places since I've given 2 sig figs in my concentration and 2 sig figs in my Ka, I get that my pH is equal to 5.47, which is D. Question 18 says the pH of a 0.14 molar solution of an unknown monoprotic acid is 5.85. Calculate the Ka of the acid. The first thing I'm going to do is use my pH, which is equal to 5.85. I'm going to use that to calculate the concentration of hydronium ions, which is going to be 10 to the negative pH, which is equal to 10 to the negative 5.85. And when I punch that in my calculator, I end up with 1.41 times 10 to the negative 6. Yes, I'm carrying an extra sig fig, but I will do my rounding at the end. Now I know that when I take that monoprotic acid and I put it in water, it's going to partially dissociate to give me hydronium ions plus the conjugate base of the weak acid. I know that initially I'm starting out with 0.14 molar of my weak acid, none of these, and then I have some change, or I'm going to lose X, I'm going to gain X over here and gain X over here, and at equilibrium I have 0.14 minus X, I have X and X here. But I know that my X is equal to 1.41 times 10 to the negative 6 molar, and I know that it's going to be the same thing for the conjugate base. Now, since 1.41 times 10 to the negative 6 molar is less than 5% of 0.14, I'm going to ignore the minus X, so I'm going to ignore this, and I'm going to say that at equilibrium I still have 0.14 molar of my HA. Now to evaluate the Ka, since Ka is going to be equal to the concentration of hydronium times the concentration of my conjugate base divided by the concentration of my weak acid, I get that it's equal to 1.41 times 10 to the negative 6 squared divided by 0.14. Again, my Ka should only have 2 sig figs in it, so I do my rounding and I end up with 1.4 times 10 to the negative 11 as being my Ka value. B.